Okay, let's go to next problem. Next problem is the 12 kilogram block is confined to move along the smooth parabolic path. Okay, the attached spring restrict the motion, and due to the roller guide, it always remain horizontal as the block descends. Okay, this moving down. Okay, if the spring has a stiffness of K equal to 10 Newton per meter and unset length of 0.5 meter, the mass of the roller and the spring can be neglected. Okay, so we would like to find the normal force of the part on the block at the instant x equal to 1 meter when the block has a speed of 4 meters per second. Okay, the rate, and the second question is the rate of increase in speed of block at x equal to 1 meter. Okay, so we would like to find the normal force and the speed, increase in speed, that is the acceleration in tangential direction. Okay, so for this case, we starting with draw the free body diagram, and we declare the problem first. For the block, okay, we may draw the free body diagram like this. Okay, because we already know the part. We already know the part. The part is a public part. Okay, it may be better to select the normal and tangential coordinate system for solving this type of problem. Okay, because we already know the part. Okay, and for the case that, just review a little bit. The normal and tangential direction. Okay, tangential direction is go to is tangent to the part. It's always tangent to the part. And normal direction is perpendicular to the tangential direction, but it's always toward to the center of curve. Okay, so for this case, the curve is here. Okay, so then normal force should be, this is the center of curve. So then the normal direction should be go to this direction, is a positive one. Okay, to set up the coordinate system, you have to follow this rule. Okay, do not set up the coordinate system in different way from this. Okay, because normal direction is always toward to the center of curve. Okay, so for this case, from the block, we draw the free body diagram. Okay, the block we have the weight. Okay, this is in vertical direction, and we also have the spring force that's keep in horizontal from the problem. And we also have the normal force that's always normal to the part. Okay, this is 90 degrees with the tangential direction like this. Okay, and it's equal to on the right hand side, that is a kinetic diagram. Let's say if we set up the normal and tangential direction here, this tangent be here from the same direction of the motion, and the normal direction is in this direction because this is toward to the center curve. Okay, so then this side should be the positive one. We set up the direction of motion in same direction of the coordinate that we already set up. Okay, for this case, if we follow this step, we draw the picture already. Okay, and the angle theta, we can determine angle theta by take the derivative of the curve part. Okay, for the curve part, we already know the equation of the part. That's y equal to 3 minus 0.5 x squared. And to find the angle theta, this is equal to dy by dx, that is equal to tan theta. Okay, from this equation, just take the derivative to this, we obtain equal to minus x now. And when we substitute x equal to 1 meter, we get tan theta is become minus 1. Okay, and then the arctan minus 1 is become 45 degree, minus 45 degree now. Okay, and if you take the second derivative to the part equation, take the derivative to this equation again, we obtain d2y by dx2 term that is become minus 1. Okay, for this case, if we follow this step, we draw the picture already. Okay, and we also have the normal force that's always normal to the part. Okay, for the curve part, we already know the part. We from the formula of the radius of curvature that is defined by this. Okay, and we substitute the value of x equal to 1 into this equation, and also y prime and y double prime. We obtain the radius of curvature is become 2.8284 meter. Okay, like this. Okay, and from this one, if we consider the deformed length of the spring, okay, we know that the deformed length of the spring, that is the position that we consider, is at 1 meter. This is a deformed length, and the problem gives us that the unstretched length of the spring is equal to 0.5. Okay, so it means that the elongation of the spring is become 1. This is the deformed length, the final length of the spring, and this is the initial length. So then this has the elongation. The spring has the elongation of 0.5 meter. Okay, so for this we can determine for the spring force, that we already know the spring constant, and for this case we find that spring force is become 5 Newton. Okay, and for that case, for x equal to 1, we can find the normal acceleration. From this case, that is normal acceleration is become v squared over rho, and we obtain the normal acceleration is equal to 5.66 meter per second square. Okay, so now we already complete the kinematic part. That we already have the essential information about the acceleration, the force in each direction. That's we now move to consider the equation of motion in 2 directions. That is in normal direction and in tangent direction. Okay, for the normal direction first, if we draw the free body diagram like this, okay, we found out, as we know, the tangent is the tangent to the part. We can find the angle theta here. That is measured from the x-axis. Okay, this is the angle theta. Okay, and if it is the 90 degree, okay, this is 90 degree, so then this should be theta. Okay, and this should be theta also. Okay, so then we decompose the spring force and the weight into normal and tangential direction to consider to form the equation of motion in normal direction and tangential direction. So if we consider the normal direction first, and we set up, this is the normal, the direction to normal is the positive one. Okay, we found out mg cosine theta. Mg cosine theta, that is for now theta. We already find that theta at x equal to 1 meter, it's become 45 degree. Okay, and fs sine theta, okay, minus normal force, okay, minus normal force here, and it's equal to MAN. Okay. And after we substitute this value into this equation, we can solve for it. That is now n is equal to 18.856 Newton. Okay, it is complete for this part. Okay, in order to find the acceleration in tangential direction, that is inward, is maybe defined like the rate of increase in speed, that is AT now. Okay, and for the tangential direction, we have mg sine 45 degree, okay, minus fs cosine 45 degree equal to MAT. Okay, we already know fs. Okay, we already know mg. We can solve for AT now, and the acceleration has become 6.642 meter per second square. Let's complete this problem.